Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So we will be continuing with our binary search playlist, which is the part of the Strivers A to Z DSA course. Just in case you haven't checked it out yet, please make sure you check it out from the link in the description because this is world's most in-depth DSA course. So till now, I have covered up till this particular problem. And in this video, I'll be covering up the problem find peak element. So what does the problem state? It states that you have to find the peak element. What is the definition of peak? It states if you take any element at an index I, it should be greater than the left element and it should be greater than the right element. Very important, greater, not greater than equal to. It should be greater than the left and should be greater than the right. So I'll be taking 4 different examples in order to explain you the problem statement in a much better way. So imagine if you take this particular array. So over here 1, 2, 3, 4, 5, 6, 7, 8. So I can say it's linearly increasing till here and then at 5, 1 it drops. I can say, so can I say this is the element? Can I say this is the element which is basically greater than 7 and greater than 5? Thereby the element 8 is your peak. Got it? So over here the answer will be 8. Now will the array only have one peak? Because in this example we just had one peak. Now remember one thing, the array can have multiple peaks. Let's take this particular example. So we have 1, 2 and then 1, then 3, 5, 6 and then 4. Can I say this? And over here can I say this is a peak? Can I say probably this is a peak? Yes, there are 2 different peaks if I carefully observe. Why do I say that? Because 2 is greater than 1 and 2 is greater than 1. 6 is greater than 5 and 6 is greater than 4. So there are 2 different peaks. Now you can return any one of them. They don't care about that. You can go ahead and return any one of the peaks. So imagine I'll return 2. That is absolutely okay. So if they are asking you to return the index, it is okay. If they're asking you to return the number, then also it is okay. So let's take the third example. Over here, if I have to draw the graph, it's linearly increasing. So if I ask you about the peak, I can't see one. So what they have told in the problem statement is maybe take minus infinity on the left and minus infinity on the right. So you will always be under this assumption that there's a minus infinity to the left of the first element and there's a minus infinity to the right of the last element. So if I see this, now can I say 5 is a peak? Can I say this, that 5 is a peak? Why can I say that? 5 is greater than 4 and 5 is greater than minus infinity as well. So for this case, your peak will be 5. Yes. Let's take another example. Over here, it's reducing. So if it is reducing, again, let's assume this to be minus infinity and minus infinity because the problem statement clearly states that. In this case, can I say this to be our peak? Why? Because it's greater than minus infinity and it is greater than 4 as well. So that's the only index where it is greater and greater. So over here also I can say that the 0th index is containing the element 5, which is my peak index or peak element. So I hope you have understood all the examples. Now it's time to think, how can we solve this? So if this problem comes up in an interview, what is the first solution that you should always give? Now what is the extreme naive solution that you can think of? I can probably think of doing a linear iteration. Yes, we can. What we will do is, we will start with 1 and we will check on the left and we will check on the right. So on the left, we are sure that it's minus infinity. So that is for sure greater than that. But on the right, we do not have 1. Then we move to 2 and we again check for the left and for the right. Then we move to 3 and we again check for the left and for the right. Then we again move to 4 and we check for the left and for the right. Then we again move to 5, we check for the left and then the right and so on. Whenever you reach 8, you'll find it out that it's greater than the left and it's greater than the 5. So if that's the case, that is absolutely okay. And this can be my peak element. So can I say this? I'll probably start with index 0. I will go until the last index. And I will be like, hey, listen. If it is index 0, I don't need to check for the left. If it is not, in that case, the left one has to be greater than array of I. Sorry. has to be smaller than array of I. Perfect. That's one of the cases. Can I say this? Either it is left, in that case it doesn't check for the left because on the left we have minus infinity. And if it is not, then I go ahead and check, is the left one smaller than this? So that's one of the cases. It has to be true. And can I say and either it is the last. In that case, if it is the last, I don't need to check for the right because the right is always minus infinity according to the problem statement. So if that's the case, I will say fine. Otherwise, this has to be greater than the right. Can I say this is another case? This is one case where we check for left. This is another case where we check for right. And this will be the overall if statement. If that is the if statement, can I say this is my peak index? So probably I can say this is my peak index. Very simple linear iteration. What will be the time complexity of this particular code? Can I say it's a big O of n because we are just simply traversing. What is the space complexity? A big O of 1. Obviously, the interviewer will not be happy with big O of n and he'll ask you to optimize this. Now this is when we start thinking. If big O of n is not working, what will work? Like what is better than big O of n? We can probably think of something as logarithmic of n. If I'm thinking about logarithmic of n, I know there are only certain number of algorithms that comes to my brain. And one of them is definitely binary search. And why do we think of binary search here? The sole reason is, what are we looking for? We're looking for something as search, which is kind of like search. And where are we looking at? We're looking at an array, which is kind of having a sorted tendency. If you carefully look, it will either be like this, then probably go down. If it has multiple peaks, again go up, go down, like in case of multiple peaks. But something I'm for sure is, it always has a sorting tendency. Some portion of it is in a sorted order. The other some portion is again in the sorted order. So I can relate. There is something as find, which is search. It is kind of sorted and the big O of n is not accepted. So all of these factors will kind of push me to think in the direction of binary search. So this is how you think of binary search. It's not that you just memorize. All of these factors, you try to submit the brute force, it doesn't get submitted, then you start thinking about logarithmic of n, and that is when you kind of go towards binary search. Got it? So how can we solve this? First of all, let's assume that the array has one peak. I'll first solve the problem where we are taking this assumption that the array has just one peak. First, I'll try to solve the problem where the array has one peak. Then we will try to expand it to the problem where the array has multiple peaks, which has greater than one peaks. So let's first try to solve this. Can I say one thing for sure? If the array has one element, imagine if the array has one element, just in case. There's a minus infinity on the left. There's a plus infinity on the right. Can I say, there's a minus infinity on the right as well. Can I say for sure that if the array is having one element, that one element will be your answer? That is very obvious. So something I know for sure is, if the array has one element, the 0th index will always be my peak element. Done and dusted. What about if the array has more than one element? That is when we start thinking, and that is when we start solving the problem. So let's quickly erase this. So I've taken this particular assumption that the array has one peak, and I'll try to solve it, and then we can expand it, okay? Now tell me one thing. What is the standard procedure of binary search? The standard procedure is have a low, have a high, and then have a mid somewhere here, and then start looking for it. We know for sure. So if I have to write down the indexes, it will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's analyze how can we apply binary search. Can I say, since the array just has one peak, so if I have to draw the graph of the increasing versus decreasing, it will be something like this, where till some portion the array will be increasing, and then till after some portion the array will be decreasing. Just an hypothetical scenario to understand it better. We know this for sure. Now, can I say one thing? That if this is happening, and if we are doing low at the starting point and we are keeping high at the last point, and imagine mid is pointing here, then either the peak will be on the right. What can be the case? Either if your mid is pointing here, the peak will be on the right. If your mid is pointing somewhere, the peak is on the left. Or if your mid is pointing to somewhere, the peak is also that index itself. Okay, I've kind of figured out certain cases. Because if mid is here, the peak is on the right. If mid is pointing here, the peak is on the left. If mid is pointing here, the peak is the mid, right? So we have kind of got our observations where we know the cases can be on the right, on the left, and on itself. We know these can be the three cases if we just have one peak. Let's try to solve this now. So I'll keep a low and I'll keep a high. And I've written down the indexes at the top. What will be the mid? The initial mid will be 0 plus 9 by 2, which will lead me to 4 integer value. And this will be pointing here. Can I say over here, I have a 5. So mid is standing at 5. The first and foremost thing we will check is this a peak element? Because according to the question, you just need to find one peak. Is this the peak element? You're like, hey, you're greater than 4. But no. This is a problem. So you are definitely not my peak element. The first check fails. Now I have to think, hey peak, are you lying on the right? Hey peak, are you on the left? We have to think in that direction, correct? So if I'm standing here, by the naked eye, I can see that 8 is on the right? But how can I write it in terms of coding? I'll be like, 5 was greater than 4, which means it's in a linear curve. It's in a linearly increasing curve. Can I say this? It's in an increasing curve. If the mid is pointing to an increasing curve, then the peak will always be on the right. Very obvious. So can I say I will never have the peak over here? Never ever. Because if it is increasing, how can an increasing curve have a peak? So the peak will always be on the right. So what I will do is, I will take this and I will just eliminate the left search space. We will move. Very standard binary search. What is the next? Index 5 plus 9 by 2, which is 14 by 2, 7th index. So let's point here. I straight away point there. And what do I get is, I'm like, I have a 8. And this 8 is greater than 7 and greater than 5. I got my peak. Finish. Over. That's my answer. So that is for one of the examples. Let's take another example with one peak. Let's understand this in a much better way. So I've taken one more example where you can see that the peak is 13 in this case. Let's again start the same thing. I will have a low here. I will have a high here. Where will the mid point to? The mid will initially point to this place. Is this the peak? That's greater, but not greater than this. So this is not a peak. If you carefully observe one thing, let's try to analyze. It's a linearly increasing, and then it starts decreasing. So apparently, the mid is somewhere in the decreasing curve. How do you realize that it's in the decreasing curve? It's super simple. You take 6, if that's basically smaller than the left element, or you can say you take 6 if that's greater than the right element. That means it's in the decreasing curve because it has to be smaller than the left and it has to be greater than the right. Then only it's at the decreasing element. So can I say it's on the decreasing curve? If it's on the decreasing curve, can I surely say I have a peak on the left? I do have. So thereby, can I say that the peak will never be here? If I have one peak, it will never be here. Thereby, the high moves here. That is one lesser than mid. Standard binary search done. What is the next job? Again, finding out the mid. This time the mid will be this portion. Why? Because 0 plus 3 by 2 is 1.5. Integer is 1. Let's see. Is this the peak element? I don't see. It is definitely not the peak element. Because it's greater than 1, but not greater than 13. That's not the peak element. Okay. Let's see the curve. 1, 10, 13 and 7. Right? That's the curve. 13 and 7. That's the curve. So 10 is on the increasing curve because 10 is greater than 1. So it's on the increasing curve. So obviously the peak will be on the right. So just go ahead and move it. The peak will be on the right. So low will be pointing here and just erase it. What is the next job? The next job will be something like finding out the mid. So the mid this time points to here. Again, standard thing. Doing a 2 plus 3 by 2, which is how much? 2.2. Yeah. That's the mid. This time, when your mid is standing at 13. 13 greater than 10, greater than 7. You got your mid. Done and dusted. So apparently I got my mid. Quite simple. Now you might be thinking, but Striver, you are kind of checking for left and you're kind of checking for the left and the right. But what happens when the first element is the peak or the last element is the peak? So if you remember, we had examples where we had something like this. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this case, if you remember, 10 was considered to be the peak. Why? Because 10 is greater than 9 and it is always greater than the hypothetical minus infinity on the right. And there was the other case where we had like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. In this case, this index was considered to be the peak. Why? Because it is greater than the hypothetical minus infinity on the left and it is greater than the 9 present on the array. So how do we deal with such cases where we are sure that the peak element can be the first and the last? Because I don't want to go on there and check on the left because there's no one on the left. So while starting, what you can do is, just for the sake of ease, just for the ease of writing code, because you will always check with, is mid greater than mid plus 1? And you will always check, is mid greater than mid minus 1? Now you don't want your mid to be index 0. Or you don't want your mid to be index n minus 1. Because in both the cases, if you take index 0, 0 minus 1 will be minus 1. You don't want to go and check with array of minus 1. Also, you don't want to go and check with array of n because they're not there. So how can you prevent this checking? Because I don't want to get into complications of writing too many edge cases. So let's analyze. What I can say is, can this element be a peak? I know this first element will always be greater than the left guy because left is minus infinity. The only thing I need to check is it greater than this? So while starting, I will say, hey 1, are you greater than 2? He says no. And I'll check 10. Hey 10, are you greater than 9? And it states, I am. So you do not perform binary search. No need to perform binary search. Just say 10, you are the peak and return. Just check for one variable. Just check for the first and check for the last. If either of this or this is your peak, return. No need to do binary search. For this one, is this greater than 9? Yes. No need binary search. Return 10. Simple as that. So you will always check for the first and the last element separately while coding it up. Got it? Now a question might arise. But Striver, then how to perform the binary search? You will say the binary search will always start from this and this. Why? Because I have manually written the code for the first element and the last element. And I was sure that they were not. If they were, I would have returned. If I am now performing a binary search, I'll just do for this section of the array. I'll just do for this section of the array. Because if I do for this section of the array, when I perform the left, when I perform the right, they will always be there because low will at minimum will be 1, high at maximum will be n minus 2. Got it? So I've shrinked it so that the overflow cases are handled. So if I have to write the code, I will go to multiple peaks, but let's write the code. It's very important to keep the code in your brain now. So I'll say function of array of n. What is the first thing? If n is equal to 1, I know that there will be like the only element, the 0th index will be a peak. Return. What's the next thing? I'll be like, okay, maybe array of 0 is my peak. Maybe. So if that's greater than array of, let's say 1, I'll say you are my peak. Perfect. Because if it's greater than this, it's already greater than minus infinity. Or else I'll say if array of n minus 1 greater than array of n minus 2, then n minus 1 is my peak. So I've written 3 manual cases. One is for the size 1 array. The other one I've written for where I'm sure that the first element will be the peak. The other I've written where the last element I'm sure that that will be the peak. Now what will I write in the next? I'll be like, okay, let's take low equal to 1. Let's take high equal to n minus 2. I will not check for the first. I will not check for the last. And then I'll go ahead and say, let's perform the standard binary search. Low lesser than equal to high, right? And then I'll be like mid equal to low plus high by 2. What's the next step? Just check. If you are greater than the left, again minus 1. See, I don't have to check for if mid minus 1 is greater than 0. All these corner cases have gone. And array of mid, are you greater than the right? Again, I don't have to check if right is overflowing. No need to check. If that's the case, please go ahead and return the mid because that is my peak index. That is my peak index. Or else what can be the case? Maybe the peak index is on the right. Can I say, if you are lying on the increasing curve, which means you will be greater than your left, that means you are lying on the increasing curve. In that case, the peak will always be on the right. Perfect. Or else there is only one case. Because if this fails, like either of these fails, and then if this also fails, there's only one thing that will be true, which will be the opposite one. So it'll be something like, if I have to write the condition, it will be something like mid is, what will be the case? If you're on the decreasing curve, it's actually greater than the right element. Perfect. In that case, you will have to search on the left half. If it's in the decreasing curve, it will be greater than the right element. So you'll have to do this. Since the problem clearly states there will always be a peak, there will always be a peak. Why? Because the left is minus infinity and the right is infinity. No matter which array they give you, there will always be a peak. So this line will always be executed. But if the function is having a int return type, you will have to give a hypothetical return type, return minus 1. This line will never be executed. But just because the function demands an integer return type. And I know there's a return type, but it is inside a conditional statement. So the program thinks it's inside a conditional. So the condition might never happen. So program thinks in that way. So program wants you to write a return statement because the data type is integer. So you'll have to write a return minus 1, but it will never happen. The program will always get terminated over here. Always. It is just for the sake of this that you have to write, because any return statement under the conditionals is not considered for this. Got it? So you might be having a self-doubt. That is, hey, we can think of this. But then thinking about these couple of cases might be tricky. Now let me tell you one thing. Since I have a lot of experience, I can think in that direction. So if you are new, then you can also solve it using like 0 and n minus 1. The only change that will happen is you directly cannot check for mid minus 1. You kind of have to write other statements where you have to check for this case And you also have to check for this case. So you have to write additional conditional statements. Thereby, that's the only reason I've written it. And that comes from experience. I did not want to write that additional conditional statements. That is why I thought, what if I can trim it down? Because I know this will only happen for 0 and this will only happen for n-1. So if I can write those cases right at the start, I think my job is done. And if I can trim down the search space, then I don't have to write additional conditional statements. Again, it will come from experience. You just cannot write like these things straight away. So do not worry about that. So coming back to the code, this code will work for one peak, but will this code work for multiple peaks? Let's ask ourselves that question. And I'll be like, will it? And the answer to that is yes, it will, with just a single change. But before moving to that single change, let me explain you why the concept of either finding the peak on the right or either finding the peak on the left will work over here. Let's analyze. So let me draw a graph and explain you why this will work for multiple peaks as well. So imagine I have multiple peaks. In that case, it will be something like increasing, then decreasing, then increasing, then decreasing, then increasing, and then decreasing, so on. And they have already stated the consecutive numbers can never be equal. So we will never have a flat line. Now tell me one thing. How was the original, for one peak, how was the original graph looking? It was something like this. And in this case, the low was here and the high was here. And we knew if this was the mid, then this was the peak. If this was the mid, which is basically this section. So whenever you were on the decreasing, slope, the peak was on the left. Whenever you were on the increasing slope, the peak was on the right. We knew that. Can that solution be applied here? Let's analyze the first case. Imagine low is here, high is here. What was the first case? If your mid is on the peak, that case will always be true. Because if you're standing at a peak and you get it, you don't need to change that case in your binary search. What was the next case? Imagine your mid is on the decreasing slope. In that case, whenever your mid was here, you knew that the peak will be on the left. Can that case still be true? Can that case still be true? Yes, this case will still be true. Why? Because even if you're standing here, you're discarding the right, saying that you're on the decreasing slope and the peak will be on the left. You're discarding the right, which has a peak. It still works. Why? Because the left has peaks. The left has peaks, so it will find it. It will find it during the search. What if the mid is on the... Let's not take it here. What if the mid is... sorry, my bad. What if the mid is somewhere on the increasing slope, which is on this one? In that case, you are saying your peak is on the right. You are saying the peak is on the right somewhere. And that still works. Because even if you're on the increasing slope, you end up discarding the left half. You will find some peaks on the right. That is why the binary search works. Because even though you're eliminating a search space with peaks, you're sure that the right search space will still have peaks. Similarly, even if you're eliminating the right half with peaks, you're sure that the left search space will have peaks. So eventually, when you trim down the search space, you will end up getting into a search space which will have one peak. When you're trimming down the search spaces, you will end up being on a search space which will have one peak, and it will fall back to the previous problem. But this particular code requires one change, and I'll give you an example via which you'll understand why does it require one change. So let's take this array. So for this you'll do the manual checks, and the low will be here, and the high will be here, and the mid will be this. We know for sure. So mid is pointing to 1. Let's see this. This will not be true because it's not the peak. Let's check this. Is 1 greater than the left 5? Is 1 greater than the 2? So none of the cases was executed. So it will fall on an infinite loop. Why? Because on this graph, you were sure that either it will be the peak, or either it will be on the increasing curve, or either it will be on the decreasing curve. But over here, there is additional case where you might be having a mid on this case. Like, what do you call this? This is not a peak. This is like reversal of peak. This is like reversal of peak. You might have this case. You have to take care of this. So you don't need to separately take care, because if you are standing here, even if you eliminate the right half, the left half will have a peak. Even if we eliminate the left half, the right half will have a peak. So just go ahead and remove this check. Or just write an else and say, I can either go to the left or I can either go to the right. Doesn't matter. Doesn't matter, because if these cases are failing, even if I go to the left, because even if I'm here, even if I go to the left, there's a peak. Even if I go to the right, there will be peaks. I'm sure about that. Thereby, just adding this will work, or you can just eliminate this thing. Because if you're not going to the right, you'll come to the left. It still works. So just a slight change, and I've explained you with a classical example. I hope you've understood this. So going back to the code editor, I have written the exact same code. So you have to write this, otherwise this dummy return statement, otherwise it might fail. So I've just written an else, no else if, and all of these things. So this is how the code looks like, super clean, and you've understood the entire concept using the graphs. So what is the time complexity? Logarithmic base to n, simple binary search, isn't it? So I will go back to the sheet and I will say this one is done. I hope you've understood this lecture, and I hope you enjoyed this, because it's important to visualize binary search using graphs, because the moment you start visualizing it using graphs of increasing, decreasing, then you start applying binary search in different problems easily. So it's very important to understand this concept. I hope you did. Just in case you did, please do consider giving us that like, because it highly motivates me. And if you're new to our channel, what are you waiting for? Hit that subscribe button, and if you haven't checked out Strivers A to Z DSA course, please do check it out. And if you haven't followed me on Instagram, Twitter, and LinkedIn, all the links will be in the description. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye-bye. Take care.